Alright, so let's get started. And we remind you that we are recording the lecture, the first hour of the lecture, so please turn your cell phones off so that it does not ring during the lecture. And also, if you need to escape the room, please try to do it on your knees. So that you don't get in the middle of the screen during Michael's talk. Some announcements. On Tuesday, John Beatty will be giving a lecture here at noon on consensus. Sometimes it doesn't add up. The next annual lecture series is on the 1st of December, in 2 weeks from now. And it's going to be given by Sabina Leonelli. And next week also, Peter Gallison will be in town, and there will be a few events organized around his work. He's showing a movie on Tuesday called Containment. You can see some of the ads here in front of the center. And in addition, there is
Wednesday.
On Wednesday, thank you. Things get confused in my mind sometimes, days of the week. And on Thursday at noon, there will be 12:30, I believe 12:30, on the 6th floor at the Center for Humanities. There is, Peter Gallison will be presenting some of his papers. It's a public event. You just need to register if you are interested in attending this symposium. So that's the events coming up, which are supported by the Center. Today, it's the second lecture of the annual lecture series, and we are very pleased of having Michael Weisberg for the afternoon. Most of you know Michael, but I will say a few words of praise about him. He's got a beautiful suit. He literally told me to mention that, so I am doing it. He's a professor of philosophy. He's also the chair of the philosophy department. He's the editor-in-chief of biology and philosophy for now 2 years. Is that right?
I think only one.
Only 1 year.
It feels like forever.
I'm sure it feels like 2, if not 5. He's also the co-director of the Penn Laboratory for Understanding Science and the co-director of the Galapagos Education and Research Alliance. Many of you know him for his work on models, and in 2013 he published a very influential book on modeling called Simulation and Similarity with OUP. He's been doing a lot of things since that book, including doing some work in the Galapagos, and that work, including movies and things around conservation. And I suppose that work will be described in a forthcoming book with Princeton University Press called Galapagos Life in Motion. And we are eagerly waiting to read that book. And he just told me that he's writing a new book whose name unfortunately I forgot. What was the name of the
Philosophy of Natural Science.
Philosophy of Natural Science, which we
I
should
didn't
be
choose
expecting
the title, yes, but
maybe in 2019. And anyway, today is going to be talking about dark galaxies and integrated knowledge. Welcome, Michael.
thank you so much. The Galapagos talk that I'm not giving, if you want to know about it, Karen is one of the co-directors of the Galapagos Alliance, so she can fill you in. It only takes a beer, I understand. So thank you all for coming today. It's really always a pleasure to be at the center. I've had many great experiences in this room, many intense and hostile questions that have always been productive and caused me to rethink my work in all kinds of interesting ways, and so I'm looking forward to that happening here. And as Edouard mentioned, this is part of a project that apparently you've been hearing a lot about because 3 of my collaborators were here just a week ago or 2 weeks ago. But this is really a new thing for me and a kind of a different model of doing philosophy of science, which might be one of the things that we want to discuss come question period. So dark galaxies and integrated knowledge, the view from 116 megaparsecs away. So just around the time that the first humans were born, a great shockwave disrupted an entire spiral galaxy. The amount of energy in this shock was so massive that it blew out the core of this galaxy and it energized the remaining stars to a bright blue color. It formed an expanding, spinning ring, and where there had once been a spiral galaxy. And of course, I just described this event as if it happened in a flash, but it really took about 1 million years for this event to happen. So that by the time the first fully modern humans started walking around, well, not quite Pittsburgh, but wherever they were. In Africa, light began to travel 116 megaparsecs from this galaxy to our own. And last May, this galaxy was seen at the Les Campanas Observatory, the Magellan telescopes, which I'll be introducing to you as the time goes on. This picture, though, sorry, it's not quite dark enough in here, but this picture is actually from the Hubble telescope. The pictures from Magellan, for various reasons, are black and white, which we can get into as the time comes. Now, this galaxy is called 2Zwicky-28. It doesn't have a name yet. Maybe one of you will think of a clever name for it, but there it is. It's this ring here, just a ring with a kind of little tail inside it, and it's a ring composed of these bright blue stars. Now, no one's sure why this ring was formed, because as my 5-year-old would say, galaxies don't come in rings. That's not a model you can buy. Galaxies come in spirals or disks, but not rings. Other ring galaxies are known, but their morphologies, as we'll see in this talk, are explained by massive disruption events that you can actually see in the field. So that, for example, we get disrupted galaxies looking like this with one-armed spirals, and that's caused by this other galaxy passing by. Or we can sometimes have rings by these absolutely dramatic and massive collisions where you see one galaxy literally punching a hole through another, where you basically get a smoke ring that remains. But a ring on its own with nothing else in the field of view, not something that's seen. So a lot of what I want to talk about today is the search to try to figure out what could possibly account for a ring galaxy like that. And astronomers don't know why this was formed, but today I'm going to talk about what I take to be quite an astonishing hypothesis, and that's that first ring, 2Zwicky-28, is formed by a collision, but there's nothing there to collide with it. So it's formed by a collision with an entirely dark galaxy, a galaxy made entirely of dark matter, or for those of you aficionados, a dark matter halo that's completely devoid of baryonic matter or luminous matter. So something like this happened, except in the case of in the case of 2Zwicky-28 and some similar galaxies, we're talking about a luminous galaxy and a completely dark galaxy. Now, there's so much to this statement, the idea that a dark galaxy collided with a luminous galaxy. What that means, how we could ever have evidence for such a claim. My goal is to unpack this statement today. That's a lot of what I want to do. But I actually want to say a few words of motivation that sort of frames for me philosophically why I'm interested in this project in the first place. Because those of you that know me or know previous things I've worked on know that I am not a physicist or an astronomer. This is something that I've come new to. And some of the reason to do this is because it's fun, but there are other reasons too, and kind of, I think, some deeper philosophical motivations for me. So to put my cards on the table, I think one of the most important lessons that philosophy of science has taught us in the past decades, in the recent couple of decades, is that close study of physics, biology, psychology, and chemistry does not reveal an interplay between deeper explorations of the world and ever more general frameworks being developed to accommodate these sciences. In fact, instead, they proceed in a disunified fashion. I think for the most part, this is not a controversial claim in the cathedral learning, although I expect to hear if it is. But even sciences as conceptually close as quantum physics and quantum chemistry just organize the world differently. And while there are undoubtedly quite general theories, especially in physics, many steps are required to connect those theories to more local models of phenomena, and many of these connecting steps are not justified from within the theories themselves. And this can be even true in places like statistical mechanics. So this is a message that should be familiar, and it's the message that a loose alliance of philosophers, including the Stanford School, so people like Suppies, Hacking, Cartwright, Dupre, Gallison, Godfrey Smith, but also Wimsatt and Geary and Levins, and of course Sandy Mitchell have been emphasizing in the last few decades. They all have argued that as a descriptive matter, unity of science is false. Our most reliable knowledge is to some degree local and particular, and that and there's of course a radical version of this claim associated with Cartwright. All theoretical knowledge is local and particular, and the models engineers use to construct buildings give us genuine knowledge. String theory, not so much. Now that's a kind of extreme version. I don't think we need to grant Cartwright's version, but I think we should grant the general description. This actual state of science is this one of disunity. And one of the things that I would like to think about is, given that we should just accept the discovery of disunity, how do we continue to think of unity of some sort as something that might be strived for, or should we let it go? That's a possible thing that we need to kind of think about. Is this a kind of regulative ideal of some sort. But I'm not going to think about that question today. Instead, I want to focus on questions about truth or realism or developing a realistic picture of the world. So had a nice argument with Nora about this just at lunch. I'm a kind of realist. I think it's kind of low-key and pragmatic, and I've learned all the lessons of my teachers, but still I think science can and should, and to some extent has developed a true picture about what the world is like. So I think there's every reason to believe that DNA molecules are helical, that Galapagos mockingbirds are the result of an adaptive radiation, that the Grand Canyon was formed by glaciers, and so forth. And I also think we can know some really general causal facts about the world. We know germs cause disease, the application of pesticide increases populations of pests, early colonizing plants are often displaced by trees that form mature canopies, polar protic, had to get this example in there, polar protic solvents speed up reactions involving highly charged intermediates, and of course lots and lots of things like this. So I've always been interested in the question of how we can learn those facts given the fact that the sciences are disunified. And before I started working on the DARK project, the Dark Galaxy project, I would have said that this is the answer. I like this tidy solution. So the tidy solution is that basically experimental approaches warrant realist licenses by pointing to observables using multiple independent lines of evidence. So Wes Salmon, of course, is famous for articulating this idea. And also overlap arguments. This is ideas sort of starting with hacking, but really developed by Humphreys and Kitcher as arguments for realism by overlapping techniques, where you view the same thing they were thinking about further away or smaller by different kinds of instrumentation. And the theoretical approaches warrant realist licenses even given disunity by robustness analysis, an idea, of course, primarily associated with Dick Levins, but also developed in all kinds of interesting ways by Bill Wimsatt. So Wimsatt, of course, for those of you that know how Wimsatt works, he would call all of this robustness analysis and 10 other things too, but that's just the way it goes in the Wimsatt world. So I like this picture of science, I think, and I would have defended it, and I kind of do defend it in other places. This is the way it works. This is how we develop a realistic picture about the world, even with disunity and with idealized models and everything else. But of course, the other thing that I learned from my teachers is that you've got to actually be committed to understanding the science as it's practiced. And one of the things that's been interesting for me is to move beyond my comfort zone into a place that's very different and really ask, is this actually how astronomers have discovered some of the most fundamental things that they believe? And also then for this really kind of cool project that we're working on, the DARK project that tries to establish the existence of dark matter galaxies, is that how they've established the existence of those entities? And so that's kind of my task for today. And that's how I'm thinking of the philosophical issues in which they're embedded. So with that, let us begin. Okay, missing dark matter. So dark matter is a classic case in many ways of the philosopher's unobservable entity. So like the unobservable entities in other sciences, it was introduced to account for the behavior of observable entities. So in particular, the velocity of stars and other galactic bodies can be inferred from redshifts, which I'm going to actually show you how that's done later in my talk. And when one started to look more closely in the 1970s and 1980s at the rotational velocities of different parts of galaxies, an unexpected result happened. So this is work that's primarily associated with the astronomer Vera Rubin, and she started just measuring redshifts of galaxies as you move from the center to the outside. And if you look at this graph, on the bottom, the graph that kind of says expected from visible disk, that's what you would expect to see if the galaxy's mass was concentrated in the center and it sort of petered out as you went to the outsides of the spiral rings. But instead, what you see is the line on the top. You actually see this flat and even slightly increasing rotational curve. So this is just a little simulation to show you the difference. So on the left is what you would expect to see. Both, this is a kind of simulation of what the rotation would look like, and the rotational curve with the distance plotted on the x-axis and the velocity on the y-axis. And on the right is what you actually see. Now, what this started to suggest to astronomers are that we're not seeing all of the mass. These galaxies are spinning as if a lot of the mass is not visible, and that the outer part of that galaxy is spinning as if most of the mass, if the outer part is actually embedded in something that's much larger. So a picture like this, where the visible part of the galaxy is the orange part there, and the blue part is the totality of the mass. So this mass that's not seen, of course, was dubbed dark matter. This is where the term comes from, dark matter, in the sense that it's somehow it's there. We know it's by its gravitational effects, but it's not seen. And as this was bared down on in a little more detail, it's not that it's just not seen, but it's not detectable at any wavelength. So whatever this matter is, it doesn't couple to any known electromagnetic radiation. So there's no detector that can be built from it, from X-rays to gamma rays and everything in between. Now, as this research continued, and this is actually going to come back at the end of my talk, other kinds of astronomical phenomena started being investigated that dark matter might say something about. And the interrelation between these ideas are something that I'm quite interested in. I know some of your graduate students are as well. So first, there's this idea that the rotation curves are flat, but also as astronomers started thinking more about their measurements of the clustering of galaxies. So you have to, if you're not used to thinking about these topics, for astronomers that think about the universe's structure, each galaxy is like a data point. I mean, can you imagine, right? The whole galaxy, one data point. That's what they're thinking about. But then that has structure, too. There's also issues about gravitational lensing and fluctuations in the cosmic microwave background radiation and hierarchical galactic structure and so forth. But anyway, dark matter was introduced. This is a representation of each dot in this image is a galaxy. So you see that there's actually structure, that these filament structure of the distribution of galaxies. So the only way to make a diagram like this, if you just put in basic forces that we know about, is to have dark matter and to have dark energy, but that's another talk. So dark matter was initially introduced to account for observational data, but it quickly became this central feature of modern cosmological models. So modern theories of the formation and evolution of the universe become characterized by gravitational interactions between an inhomogeneous distribution of dark matter imprinted on a universe that emerges from this inflationary period from the Big Bang. And these are called lambda CDM models, lambda cold dark matter models, because the lambda is the cosmological constant, and the cold and dark matter is dark matter that doesn't move very fast. Now, what's interesting for our purpose, this is just another representation of the the universal distribution of dark matter through the universe. Now, this kind of funny-looking diagram here is a merger-true diagram. So what's interesting, if you start thinking in the terms that I've been discussing, thinking that every luminous galaxy that we see is embedded in this halo of dark matter that's 10 to 20 times its diameter, that means that to a first approximation, the galaxies are just dark matter. The luminous matter is like the icing on top of the cake. And so if you want to actually have a theory about even galaxy formation, a theory of galaxy formation really becomes a theory of dark matter halo formation, or these dark matter disks that form. And so the idea then is that galaxies actually form by first the condensation of dark matter into larger and larger halos, and then ultimately this huge gravitational potential catches the luminous baryonic matter. It falls into this halo's influence, and then ultimately it cools, dissipates, collapses, forms visible stars and galaxies, and starts spinning. Now, this is a huge subject matter, but the thing I would just want to emphasize is that once you start thinking about dark matter just dominates all of the discussions of matter. And such that this is, when people think about galaxy formation, they're really thinking about dark matter first and foremost. Now, modern cosmological models actually give us the approximate ratio of dark matter to luminous matter. And you can see here, dark energy, which I won't talk about, is 72% of the mass energy of the universe, dark matter 23%, and the luminous matter about a little under 5%. Excuse me. So dark matter is most of what's out there in terms of the matter. So if you know that the universe is dominated by dark matter, and then you know that all of your luminous galaxies are sitting inside halos of dark matter, one of the things you might be able to do is to try to account for where the dark matter is by looking at galaxies. So one of the projects that astronomers are engaged in is to try to keep track of how many galaxies are there in the universe and how much dark matter is in the universe by doing these sky surveys. So the idea is you look at part of the sky, obviously restricted by where you are on Earth, and then you use that as some kind of a statistical sample of what's out there. And then when you do that, you can make an estimate of how many galaxies there should be, how many galaxies of different sizes there should be, and then how much dark matter should be there, because all the galaxies are sitting inside halos of dark matter. So the kind of basic picture is each of these halos of dark matter should have captured luminous matter, so we can see them. You can't see the dark matter, but you can see the luminous matter. You take the sample that you get, and then, just like we do in the rest of science, you infer outwards towards the whole from the statistical sample that you have. Now, when you do that, you find out that only about 15% of the halos that cosmological models suggest should be out there are accounted for this way. So 85% of the dark matter is unaccounted for when in this method. And it's not just that you get a distribution, it's not just that you get, well, you're off by this large number. There's also the models of these merger tree models that give you the formation of halos. They tell you something about the distribution of halos of different sizes, and hence the distribution of galaxies of different sizes. And at some of the masses, in particular the very large and the very small, the estimates are off by like 100 times. Now, this problem, it's called the missing satellites problem, has led some people to say that this whole thing is barking up the wrong tree. The dark matter model, something might be wrong with that, but certainly this kind of underlying cosmological idea, the lambda CDM, something might be wrong with that. And there's, I don't know if you've had in your recent conference anybody defending alternative theories, but there's certainly more and less serious defenses of alternative cosmological theories. The less serious people, of course, are more fun, but the difficult at parties. But the more serious people think that this is a real problem and has to be accounted for somehow. And there are questions, can you fix this by tweaking? Can you fix this by adding another factor? But a lot of that doesn't quite really get to the problem, because the problem is quite severe. 85% of the dark matter is not accounted for, and in some, in some parts of the scale, you're off by like 2 orders of magnitude. So one of the biggest questions from astrophysics today is, if this basic picture, the lambda CDM picture that there's a lot of independent evidence for, is right, where is the rest of the dark matter? Where is it hiding? Is it just that we haven't seen it, or is it hiding somewhere? And so that's where we come in. Where are the rest of the predicted dark matter halos? Are they something that we can find? That's what we would like to try to figure out. So when you ask where the rest of the dark matter is, there have been a lot of possibilities that have been floated. In the interest of time, I will not discuss these in any detail, but here are some of the special pleading that's out there. Halos exist, but have attracted baryonic matter, but star formation has been suppressed. And so basically, you have some matter there, but there aren't any stars, and they're far away, so you don't really see much. For small halos, supernovae have ejected all the dust and gas, leaving first-generation stars only, again, so kind of too dim to see. And similarly, for large halos, there are these supermassive black holes that could have depleted all the gas needed for star formation. And then there's also this idea that there's just a lot of almost dark galaxies that have hydrogen and no stars. If you want, I can talk about any of these in questions. But in all of these cases, I mean, people have looked and not found much. So the group that I'm involved in, and I think, as I said, many of you have met the collaborators, has a much simpler suggestion. And the simpler suggestion is this. Missing dark matter halos exist as completely dark galaxies, namely halos that have no baryonic matter. So they never had it, or they had it early and they lost it, and they're just floating out there as completely dark galaxies. The collaborators that I'm speaking of are Barry Medor, Melissa Jacquart, and Maya Seidel. This is a really interesting philosophy, astronomy joint project. So there are 2 PIs, an astronomer and a philosopher, and then 2 postdocs, an astronomer and a philosopher. And the theory behind the collaboration is that we all learn about each other's business. And so it's happening slowly but surely, and it's quite interesting, actually. And that itself is an interesting talk, negotiating all of those kinds of issues. Many of you are familiar with this from other kinds of collaborations, but when you're very, very, very tired at high altitude and there's bad weather, so you can't open the dome of the telescope, I think that they get a bit tenser than you might have thought otherwise. So, okay, we think that all of the missing dark, we think a lot of the missing dark matter might be in completely dark galaxies. And that's an interesting claim, so how might we test it? So our pre-project theorizing was motivated by luminous-luminous interactions. So we knew already from previous work that galaxies can interact with each other. So you want to observe something that you can't see, like dark matter. You have to look at for its effects. Well, what could its effects be? Well, some of the effects are going to be it's got to be on really massive things. So one of the really massive things that we might see are its effects on other galaxies. So here is galaxies interacting with each other, and we know that sometimes, as I mentioned before, galaxies interact in these dramatically collisional, violent kinds of ways. So for example, this is ARP 147, and in ARP 147, you have, this thing is just a foreground star, but you have this ring galaxy, and you actually can see here this disk galaxy that is punched through it, and then the orange part there is probably the original nucleus of this galaxy. But there's a traversal from this disk galaxy through the ring. It blew the ring up to a much larger size than it would have otherwise been, increased its rotational velocity massively, energized all those stars. Notice almost all of those stars are blue, and this has kind of been well characterized. There's also some there's a characteristic clumpiness of the blue stars, but that's again we'll see this a little bit later. So our idea, the dark galaxy hypothesis, in order to actually test that, we want to try to find this situation, but where we don't see the optical collider. So we see the collidee, but not the collider. So the question is it possible to actually look for a situation where a dark galaxy might have actually interacted in this way with a luminous galaxy, where you'd see the dark galaxy colliding with the luminous galaxy, and could you characterize that somehow? One clue, of course, would be that you see a characteristic signature of a collision, but without seeing something that could have done the colliding in the image. So that's the kind of pre-theoretic intuition. So this project goes kind of like this. So this is a collaboration, like I said before, with the observers at the Carnegie Observatories. And the project proceeds in 3 stages. So stage 1 is to try to characterize what that kind of a collision would look like. What would it mean if you had a dark galaxy colliding with a luminous galaxy? What would its effects be on morphology? What would the effects be on velocity? What would the effects be on star formation, and so forth? The second step is to actually then examine the astronomical record and see, can we actually find any examples that look like that? And then the third step would be to actually do new observations. So just to kind of then give you, I'm going to basically do an initial pass through this and then talk about some of these issues in more detail. So first, trying to characterize what I want to call signatures. Signatures being the characteristics of this interaction. So we began with these fairly, I'm going to call them simple simulations, but they are definitely not simple. But basically, astronomical simulations that are numerical simulations are, they're discrete approximations of fluid mechanics. So I know a lot of you in here are interested in climate simulations, so you're very familiar with this kind of thing. These tend to be particle-based simulations. And so here, just show you, here's a really simple one. You're going to see, this is actually a luminous collision here. So that was done with a program called Gadget 2, which is you see the ring formation there. So that would be like that ARP 147 that we saw. Here is an early attempt at a simulation with a dark matter halo and a luminous galaxy. So the red, you're seeing it from different angles here. So the red is looking at it from above, and now you see it from the side, 2 different directions from the side, and you see the halo passing through. And we see this kind of, again, the characteristic ring formation. And then finally, let me show you, and again, I'll come back to this a little bit later, but this is the simulation that we're actually using. This is using something called called Gizmo. We were using Gadget before, called Gizmo. So Gizmo is a magneto-radiation hydrodynamic plus gravity simulation, and as I said, they're discrete particle approximations of fluid dynamics. So again, those of you know your General circulation models know how this is usually done, right? There's a grid that you impose, and inside the grid you parameterize. Outside of the grid, you actually do physics. So what's cool about this is it's gridless. So the way that it had gone before is you get your grid, and then people make the grid smaller, or maybe a different shape, or dynamical. This is actually gridless, and the reason this is really cool, I know John's going to like this, is because the grid, a lot of the grid approaches don't conserve angular momentum, which is a really big problem, right? And it turns out then you can actually do really interesting, like this would be a great philosophy paper just by itself. You can do really interesting simulations on very simple problems, like, what does a fluid look like going around a cylinder? And you can do it with the different approximation methods, different kinds of grids and gridless methods, and actually see how much distortion is in it. So you can almost do, you sort of can do, it's like a kind of robustness testing with known problems, some of which, I don't think any of them are solvable analytically, but some of them are like, you can do a lot of real detailed mathematics on them. So that's kind of what this group has done, making this gizmo. And it does allow for the conservation of angular momentum, and so we have more confidence in these simulations. Melissa Jacquart's work in this area has largely been on trying to think about everything that goes into the inferential power of these simulations, all the approximations and idealizations and how they're handled, and how that's actually used to enhance the observational part. So that's kind of an interesting piece. Again, I'll come back to it. Second step is this hunting and looking through the record. So we can use simulations to tell us something about the morphology we're looking for. But the morphology we're looking for are basically rings, right? And so how do you find rings? So there are nowadays several projects that are sky surveys. They used to be done manually with plates and people looking by hand. Now they're somewhat automated. This is the Sloan Digital Sky Survey 3. It has 200 million astronomical objects in it. So of course, no one could really look at all those objects. But luckily, there are lots of amateur scientists out there, and amateur scientists like to look at pictures and click buttons. So another piece of this kind of whole puzzle is the citizen science piece. So if you've talked to Karen, you know that there's different grades of classiness in citizen science, from the really cool stuff that we do in Galapagos to just getting a large labor force. This is the getting a large labor force kind. We have 200,000 images, and machine learning is not good enough yet to look at all of them, although maybe in Pittsburgh it is, so this is something that we could talk about collaborating on. So you use citizens instead to go and you click on buttons at what these images look like. I'm afraid that the output from the citizens are not as good as you might like them to be. Nevertheless, if you allow for lots and lots and lots of false positives, because we really don't want any false negatives here, you can actually start to come up with interesting lists of objects that you might want to look further at. So it's basically this gigantic collective effort at looking. So when you give the citizens that, happy to know that they came up with one of the ones that we already knew about, 2'Wiki 28. That's one of the things that you'd like. They also came up with ones that we didn't necessarily know about. This was a known object, but we hadn't really thought about it. ARP-Mator 2134-471. So this one, I'm sorry, it doesn't really show up with the light in here, but there's definitely a ring, and the nucleus is definitely offset, so it's not quite as clean as that other ring. But we've come up with a dozen or so objects that look like this. And then the real fun begins. And the real fun is to take those objects and actually begin to study those in a really serious way. And now I'm going to, rather than just tell you about where we're studying them, I'm also working on a film project, so I'm going to show you a little piece of that to introduce you to our field site.
Once was a philosophy major, yeah. So I have the BA to prove it. Yeah. I don't know, actually. The dark matter problem that we work on could be construed as a philosophical problem, I suppose, since we're all studying a substance that we don't see, feel, or sense except through inferring its existence from gravity.
So the voice in the video is Matt Walker. Do any of you guys know him at CMU? So you should get to know him. He's an assistant professor there. He's actually there today, so that's why he's not at the talk. But it was just audio we caught when everybody was frustrated that the weather was bad. But seriously, that's a thing, right? It shouldn't be a thing in Chile, but it's been, the planet is messed up, you might have heard. So the weather's been bad there. So anyway, it gives you a little taste of the scale of these telescopes. They're 6.5 meter telescopes. So think about that mirror. So it's basically 6.5 meter mirror and another mirror. So the 6.5 meters, they drink light, and then they reflect it up to a secondary mirror, and then there's a big digital camera in the middle. So this is they're called the Magellan telescopes, the pair of them. Boy, this room isn't best for astrophotography, but I hope you can see. It's very, very clear in the skies. This is above the Atacama Desert. So it's you're high, 8,000 feet, and the sky is very clear. And if you like the southern sky, you see a lot of it there. In fact, it's actually hard to pick out the Southern Cross. The stars are so bright. But you can see the Magellan Clouds in this picture and the beautiful pictures of the Milky Way. So it's a very cool telescope if you're into instrumentation. So it's not just a 6.5 meter mirror. It's got adaptive optics. So there are little actuators in the glass that are in real time changing the glass to compensate for atmospheric distortion. So there's basically, you always have a guide star nowadays on a modern telescope, so you don't just move it by time like the old telescopes. You actually move it by tracking this guide star. And then the guide star, the computers know what it should look like on the mirror, so the mirror is being distorted to actually try to resolve the image onto the glass so that it looks as sharp as it should look, and then that's why the image is kind of being preserved as well as it is. So these are exceptionally good telescopes. Just to give you a sense of why do we have telescopes in the ground? The Hubble telescope's 100 inches, so it's 2.5 meters. So there's of course no distortion for the Hubble, so it's great in many ways, but these are just, can see just much further. The telescope that's being built now is a 25 meter telescope, so you could just imagine what that telescope will be able to do. As I said, and I think this is actually important for part of the story I want to tell, so the way it works is that basically you have this thing on the bottom right is a gigantic digital camera that has 8 sensors on it, and they're you can move various sensors into the guide path, but this, I don't have a mouse here, but this gives you a sense. There's these 8 segments, each of which is, think of a digital camera sensor. That's what it looks like before it was put into the telescope. So it's, again, a giant digital camera. And this is actually first light from the telescope. So it's the first galaxy that was seen. These are charged coupled devices. Do you all know how that works? So basically, photons accumulate on the surface, builds up an electrical charge. Imagine that there's a little capacitor at each segment. And then when it's read down, the charge is just basically moved across, and it's kind of read in strips. So that's just how your digital camera works, except that this is much more sensitive. In fact, it's so sensitive that you can, if you have it just blacked out, you see all kinds of stray cosmic rays and things like that, because you can turn it up quite high. But our exposure times are sometimes like 10 minutes. So it's as sensitive as it is. When you want to look at something that's 118 megaparsecs away, you do need to actually allow the photons to accumulate. All right, so then, you see this is in black and white, and it's because just the absolute basics of how all this works. Your digital camera sensor is also in black and white. It's just that each sensor has little filters in front of it, and there's a red, blue, and a green filter. And the same thing can be done here, but rather than putting little sensors in front of each pixel, we have the surface, just be maximum resolution, and then we can slot in filters of different colors and actually construct the color image in a way that your digital camera is doing it automatically, but you're losing. If you actually just took just the gamma channel, just the brightness, you'd have 3 times the resolution. You're losing it by having them divided into 3 different color sensors. All right, so this is kind of what it looks like when you get a galaxy on the screen here, and we'll be going back to there in a second. So as I said, this project has these three parts: characterize the signatures by simulation, citizen science supported search through the Sloan Digital Sky Survey, and then these careful observations of candidate galaxies looking for their characteristic morphology and dynamics. Okay, so how do we, how does that, how does that really going to work? What I want to spend most of the rest of my time doing is thinking a little bit about the epistemic issues that each of these stages of the research raise. So I want to kind of circle back to these issues that I opened with. Don't worry, I have more to say about the cool astronomy. But really what I want to begin to focus on is how we could ever really begin to nail down this kind of astonishing claim, or for that matter, claims about the discovery of dark matter in general. Okay, so the first thing to say is that observing any astronomical object involves moving beyond our senses and even augmenting them. So there's actually this nice quotation I like from Paul Humphreys. He says that one of science's most important epistemological and metaphysical achievements has been its success in enlarging the range of our natural human abilities. And that's, of course, he's making this claim kind of generally in the sciences, but it's especially true in astrophysics. So few fields have harnessed the power of technology and computational power to extend our senses across time and space and sensory domains as extensively as astrophysics. We can look 118 megaparsecs out. We can look from X-rays to gamma rays and so forth. Now, why does astronomy require so much augmentation? Why has so much effort been put into it? Astronomy is as much about engineering and spy technology as it is about astrophysics. You know why spy technology, right? Maybe we should better turn the camera off for this. So all those good telescopes in space, you know what they really are, right? They're spy satellites that are turned the other direction. So the story should be written about all this. There's good stories for beers about these subjects. The Hubble telescope is a very modest spy satellite. But really, why is this necessary? Well, galaxies are not only far away, but they're enormous, right? They're 100,000 to 1 million light years in diameter. And of course, there it is on our sensor, right? Cuts across them, but that's an enormous object. And so one of the things that's really interesting is, what do you want to do? So you could try to get extremely detailed information about a tiny slice, or you can highly compress and get kind of the average of the whole. And so the latter course is taken in a case like this, and there are other ways of focusing on a tiny piece of that. They're actually basically fiber optic cables that are put into the sensor path to just look at a tiny part. But of course, even a tiny part there is still maybe 100 light years across or something like that. But you're integrating over a huge amount of things. So they're very big. They're very far. These events happen in time, right? We often talk about these things as a flash, but like these rings that we're talking about form over the course of 1 million years. They take place in the past and take place in the past, and there are no experiments, but there are staggeringly large data sets. And just to focus on those last two for a second, so on the one hand, you can't do an experiment in astronomy, and so like other kinds of historical sciences, it feels limited in certain sorts of ways. But unlike other kinds of experimental sciences, non-experimental sciences, unlike other kinds of historical sciences, there are staggeringly large data sets. So in paleontology has the same kind of problem, but you don't have the entire universe to look at. So most astronomers will tell you that if there's something that can happen physically, it's happened somewhere, and we could probably detect it. So while you can't manipulate something causally, you could probably find the right causal setup to observe it. And that's a kind of interesting, if that's true, it's an interesting epistemic position to be in. Now, of course, you have to find it. So how do you find it, given that the sort of blessing of any configuration that you want being out there is also the curse of just enormous amounts of data? So the traditional way that it was done was by sort of a structured search of a small piece of the possibility space. And this is still how things like supernova detection are done. They're basically, you decide on some part of the sky that you want to look at. Sometimes it's just certain objects that you look at again and again and again. Sometimes it's certain characteristic parts of the sky, and then you look for a change. This used to be done by hand. There were it's an interesting artifact. No one would use this anymore, but it's basically an A-B. You know the mode in Lightroom or Photoshop, the A-B comparison? There are these devices that would compare two photographic plates taken of the same object, and you just go through, you could spend days as a graduate student just comparing plates, A and B, and looking for a change. This is supernova. I do need to consult my notes. 1987A, and you can see on the right is where the star was before it exploded, and here it is on the left. And this is still done. I mean, this is done by, it's partly automated now, but there are a lot of the kind of interesting citizen science projects that are looking for these kinds of things. And then as soon as you see one, everybody calls their friends up, and all the telescopes go and point at it. Another way that you can look for really exotic things is by traditional sky surveys. And traditional sky surveys were published in books like this. So Barry Mador, who was here 2 weeks ago, was one of the authors of A Catalog of Southern Peculiar Galaxies and Associations, a great title of a book, if I might say so. And basically this is, we've done all these, observed thousands and thousands of galaxies. Let's take the weird ones and write a book about them. So that's, again, a job that no one has anymore. But nowadays, there are these automated sky surveys, like the Sloan Digital Sky Survey. And the idea here is you go for coverage and not for resolution or depth. So you're scanning a lot of the sky. This was done over the course of, I can't remember how many years, but it was like 2 or 3 years. There's a northern and a southern. And now, of course, there's 20 million objects to be looked at in databases. And that's why there's this citizen science part. The next generation of sky surveys like this, though, is going to do the same coverage, but every couple of days. So they're saying it's going to be like a petabyte of data per night, or something like that, something like shocking like this. So of course, all the stuff that we're talking about is going to have to improve, and there really will need to be machine learning, because the idea here is to have a time series, so you really would catch those supernova and everything else that's happening in the sky. But I mean, that's just kind of, really shocking. But the point is that, these data sets probably do contain the sorts of information that you'd want for most astrophysical purposes, but unlocking that information is very, very difficult. And so the only way that we've found to do it so far is enlist, hordes of unwashed volunteers. And I mean, really, I'm going to talk at the end of my talk about kind of these like epistemic intensifiers. So that's a crucial one for us, but it's not a very good one. And so there's all kinds of issues there, and it's a big challenge for the next generation of astronomers. Now, the other thing that is important for our story and comes from this, again, kind of comes from people like Humphreys, are that we have to extend our senses, and we often do that by what Humphreys calls extrapolation, conversion, and augmentation. And the idea is that we move from fairly conventional observations, the observation of the visible, to these other domains. And the reason I'm just showing you the Crab Nebula here is because you're actually seeing different aspects of the nebula here. In some you're seeing star formation, some you're seeing gas, and some you're seeing dust. But you actually can see, in some of them at least, overlapping morphology. And this is something that astronomers are often doing, is they're creating different kinds of telescopes in different domains that are actually overlapping with one another. So that's a way that astronomers have used to actually augment their senses and to project beyond it. And largely, many of the objects that astronomers that study, many of these exotic objects, pulsars and nebula and neutron stars, are actually justified in this way by these overlap arguments between the kind of familiar things that can be observed through optical telescopes and what takes more exotic kinds of interventions. But what's interesting for our case is that dark matter is really different. We can't do this kind of thing with dark matter because dark matter is inherently incapable of being observed because no radiation can couple to it. So these kinds of overlap arguments that are, as I said at the beginning of the talk, often invoked in discussions of how you can be a realist even with multiple models or with disunified science, and how you could be a realist when you're far, far, far from the kind of ordinary observable domain. They're just intrinsically not available to us. So if this was the only way to warrant extending our senses, the project of searching for dark galaxies is just a fool's errand epistemically. But I think there are other ways to justify the warrant. The obvious thing that comes to mind, and again, something that Wes Salmon wrote extensively about, was Brownian motion. So chemists were not convinced initially by the existence of atoms by overlap arguments, but they were by these indirect effects. So they looked at Brownian motion. Einstein calculates really precise details about the stratification of particles in a column where Brownian motion is sort of responsible for the uplift and gravity for is it called fluctuation when it settles? Fluctuation, I think. Fluctuation, no? That's what we call it in brewing, fluctuation. Not fluctuation, fluctuation. And that allowed, Avogadro's number to be calculated with careful measurements of Brownian motion. So you might think that this is kind of what the dark matter projects, the dark galaxy projects like. We're studying dark matter by its effects. It's a lot like studying Brownian motion. But it's really different, actually, in really fundamental ways, because although maybe atomic reality was sort of initially justified this way, that's not at all why people accept atomic atoms anymore, or atomic reality. So the main reasons that people accept that atoms being real are things like spectroscopy and atomic force. This is the scanning electron microscopy. It's the fact that the causal properties of atoms are known and that atoms can be manipulated. Well, that's just not going to cut it with dark galaxies. So if you want to say that if the dark galaxy project is successful, we get it to early 20th century atoms, maybe you could go that far, but it sure doesn't look like it gets anywhere near the reality that we attribute to atoms. All of us except for Nora, apparently. Do you think atoms are going to? Okay. So now I want to let one of my collaborators chime in here. So this is Barry talking about these issues.
This particular galaxy is not unusual, but it's made up of bright young blue stars and fainter red, so-called population 2 stars. And what Maya is doing is looking and trying to synthesize that galaxy and understand what is contributing to the mass and how the stars are responding to that mass and what might be left over that can be attributed to dark matter. Now, if she had started this project by using data from a satellite that was launched about 15 years ago called Galaxies, it was imaging galaxies in the ultraviolet light that never makes it through our atmosphere. It's cut out by the ozone layer. And in that case, she wouldn't have seen any of the red stars at all because they're not putting out any ultraviolet. And there would have been a big, huge hole in the center of this galaxy. She would have seen the spiral arms where the hot stars were. And she would have measured the kinematics. She would have taken her spectra. And she would have concluded that there's dark matter in the center of this galaxy because she wouldn't have seen red stars. So for her, Maya, the ultraviolet astronomer, dark matter would have turned out to be old red stars. Now, if Maya, the radio astronomer, had made a map of this galaxy looking in the line of neutral hydrogen, all she would have seen were the beautiful spiral patterns of the galaxy, which leads to the formation of the blue stars, but she wouldn't see the blue stars either. She would have done the kinematic analysis and found the rotation, and she would have concluded, whoa, there's dark matter inside of this galaxy. There's no gas in the center. There must be something else that I don't know about. And she would have concluded correctly that there's something missing. And what was missing for her in that case would have been all stars. She would have discovered the existence of stars when she had her universe would have been totally neutral hydrogen. And we're in this situation where we know about the stars, we know about the red ones, we know about the blue ones, we know about the gas, and it still doesn't work. So then we postulate that there must be some other mass in addition to that. And what Maya's trying to do is find out what the distribution of that dark matter, that additional component is within this galaxy, using detailed studies of the distribution of what is known and using the detailed kinematics of what this particular galaxy is doing.
Okay, so I think what I just wanted to focus on is, it's even worse, right? So really, dark matter, and this is from, you don't have to trust me, this is from an astronomer, is dark matter is kind of the I know not what. It's there's got to be more mass here, but we don't know what that mass is doing. And we don't know any of its properties. So it looks pretty bleak. So first I said maybe it's as good as atoms in the beginning of the 20th century, but then it's I know not what. All right, well, good thing I'm running out of time, so I don't have to answer all those questions for you. But I think there's some hope. So basically, the hope lies like this. It's not just the I know not what, because there are, first of all, really important, it's not just that the interactions between luminous galaxies with other luminous galaxies show rings, but there are quite detailed signatures of these rings. I've already mentioned the ring, obviously, and also if you look at that, this is the Cartwheel galaxy, another collision. There's these bright blue stars. That's very characteristic. That means highly energetic stars. Lots of energy has been transferred to the stars. And then a few more features are there's a compression of the gas due to a shock wave. There's a characteristic rotational velocity, and also take a look at almost like these spoke-like structures. And again, you can see that if you look here. This is another luminous collision on the left. This is Artmater 644-741. You can see the spoke structure. It's kind of light here. You see the blue ring. Here we have in the middle the actual kinematics, and on the right we have a simulation of it. And now look again at our collision in the simulation. There's the dark simulation, or the dark luminous simulation, and again we get the same kind of thing. You can't tell that it's blue because the colors are not matching the colors of the stars, but you can see the formation of the ring, the rotational velocity increasing, and the formation of this star structure. So we're looking not at pictures, and we're not looking just at I know not what, but we're actually trying to look at these kind of charismatic signatures. And the charismatic signatures are things that actually quite quickly narrow down the possibility space. And so it's not just, Salmon emphasized, of course, with Brownian motion that a very small deviation from the distribution that Perrin actually measured would have led to a very, very different Avogadro's constant. But this is a case where a small deviation from these kinematics and morphology that we're measuring would suggest that there wasn't a collision at all. So that's, I think, a lot of constraint that's coming from these simulations. And the simulations are adding a lot of power to the observations. So what's the current status of this before I sum up? Well, we have some data, but our last observation run at, I might add, $50,000 per day was impeded largely by bad weather. But one of the things that we have to do is not just to take a picture of the ring, but actually bring a slit across it and actually measure. What you're basically doing is actually measuring the redshifts. I'm not going to actually show you these videos in the interest of time, but I can in the question period. But you actually can see in this is what it looks like when you're doing spectroscopy with a telescope. So in these bands here, you're actually looking at, this is how the redshifts are measured. So if you notice, they're actually tilted, and that's actually showing you that the one side of the ring is moving at a different velocity than the other is. They're kind of bended and tilted. So we're gonna see soon. But the point is, we're not just looking at pictures. We're actually looking at kinematics, and we're actually looking at particular signature morphologies. So just coming back to this kind of issue in the finality. So I said that I kind of had started from this idea that despite the disunity of science, two kinds of moves would allow us to construct some kind of a realistic picture. That experimental approaches warrant realist licenses by pointing to unobservables, using multiple independent lines of evidence and overlap arguments, and that theoretical approaches warrant realist licenses by robustness analysis. So I don't think that much of this is applicable in our case. The independent lines of evidence, I think, is, but not the overlap arguments and not the robustness. So I think instead it goes something like this. First, the existence of dark matter has to be established. And that's established by some kind of inference where evidence from these different sources, from rotational curves, galaxy clustering, stellar velocities, lensing, the cosmic microwave background radiation, and the hierarchical galaxy structure somehow converge to suggest that dark matter must really be real. And then from that and other observations, we get this background cosmological theory, lambda CDM. As I say, I think there's elements of these salmon-like inferences, but not really, because in this case, multiple independent lines of evidence, but they don't necessarily, they're pointing to dark matter. Sorry, I'm losing how I wanted to explain this. They point to dark matter not in a direct kind of causal way. Instead, it looks more like something like an inference to the best explanation, but really each of these things have different kinds of explanations. It really looks more like, if you ask an astronomer, something like, they say an inference to the only explanation. What they really mean is something like a unification argument, that only dark matter can actually simultaneously explain all of these things in a reasonable way. And given where I'm giving this talk, I was giving some thought to the question of, can we think of this as the material theory? And I'll be very curious if this comes up in questions, but it seems like it can in some ways, but in other ways, what's funny about this kind of inference is nothing's known about dark matter, except that it's the I know not what. So it doesn't fit the standard material theory picture, but maybe something about the kind of background physics that you say, well, I don't know what it is, but it obeys gravity. So I think the space of inference is going to be in this kind of unification or material theory. But let's discuss this perhaps in the discussion. But then the dark galaxy projects like this, the inference went something like this. Once we've established dark matter and once we have lambda CDM, that gives us a distribution of dark matter halos, both a distribution of mass fractions and a distribution of halo sizes. And then the idea is that that just does not match the galaxy size and distribution. And there's only really three possible explanations for that. You could reject the theory that gave rise to that, which is what the Mon people want to do. You could say that the halos are there, but they're just really hard to see. Or you could have our view, which we think is the simplest one, is that a lot of them are just actually dark galaxies that for whatever reason don't have any matter in them. And then why do we think there's evidence for this? Well, because first of all, we have homologous collisions that are luminous, and also because we have simulations, and those give rise to these very, very, very specific signatures. And those signatures, along with seeing that it's a ring or a one-armed spiral that doesn't have a visible companion, and if we're really lucky, some background gravitational lensing, that seems to be the structure of the inference that leads to the dark galaxy hypothesis. But along the way, as I was saying, it's not that we're doing robustness analysis, because it's not a convergence of different models. It's that there are these interesting sources of amplification. So had I had more time, I'd tell you about all the really cool techniques that are used to make the detectors more reliable, or the way that simulations are used to actually interpret that what comes off the detector, or the way that spectroscopy is done, or the way that different parts of the field can be isolated, or the epistemic power that comes in a low-grade way from doing citizen science. All of those things seem to amplify this inference that has at its base a just kind of basic, two things crashing into each other in a gravitational way sort of picture. So I think in sum, I want to say, that there's no way to construct an overlap argument. Multiple sources are used to gain epistemic power, so there is this bit of salmon flavor to it, but they include these kind of funny things like treating sky surveys as unbiased samples, and crowdsourcing, and simulations of increasing complexity, idealized models, and technology, and signal processing, and all kinds of qualitative reasoning and back-of-the-envelope toy models. And a lot of sitting in the control room is saying, well, could this be a candidate? Well, maybe yes, because it's within this many it's within this many rings distance, so it could still be it could still have survived. Whereas if it was a little bit further, then there's no way for that galaxy to have survived for that long. The lifetime is too long. So there's a lot of that kind of thing going too. But what's really important, I think, is that there's neither foundational theory nor robustness analysis that goes to establishing a hypothesis like the dark galaxy hypothesis. So the story is a lot more complex than the one from which I started, but it does suggest, I think, that there's hope to piecing together a realistic picture of the world. This is obviously scratching the surface of this incredibly complicated story, but I think it's worth doing. So what of 2's Wiki 28, 400,000 years after the light in this picture was produced, do we know what it means? I think the answer is not quite yet. The pieces aren't all in place, so we'll have to use our imagination this evening. But there are really good reasons to believe that 1.5 million years ago, an entirely dark galaxy smashed through a luminous galaxy, leaving us this ring of bright blue stars. Further lines of evidence, I think, will converge on this fact, but I admit it's just something that I think or I hope. But in doing that, I hope that it really teaches us something profound about how we can get some kind of a unified picture of the world from these disparate, disunified bits of science, and also how we can learn to observe something that we can't see. Thank you very much, everybody.